So pyramids is the contents are, we are talking about two kinds of pyramids. One is called Gaussian pyramids and Laplacian pyramid, and in that there will be two major operations. One will be called reduce, which is essentially reduce the resolution, and others called expand, which will expand. It will make it twice as much in x and y. So I'll give you a couple of applications for the Laplacian pyramid, one in the compression and other one in image compositing, and then we'll go back to see how we can use the pyramid to compute optical flow, and in that we are going to use this notion of interpolation and talk a little bit about that. So pyramids is a very nice way to represent images, and it's built by using the multiple copies of the same image but of different resolution, and each level in pyramid is 1/4 of the previous level, and because we are reducing half in x and half in y, and the lowest level of pyramid is highest resolution and the highest level is of the lowest resolution. So pyramids look like this. So if you start with the highest resolution, say 512 by 512, you go from there to 256 by 256, 106, 28 by 128, and so on. You keep going. Here you have 8 by 8, 4 by 4, 2 by 2, and 1 by 1. So if you take all these copies, put one on the top of each other, and then it looks like a pyramid. Like pyramids you have seen, say Egyptian pyramids. Okay. So as you see here, that given this pixel at this level, that is depending on the roughly the 4 pixel at the bottom level. Okay, and if this is ij, then we have 2i, 2j, and we have these corresponding pixel close to that, 1 pixel on the left and 1 pixel on top, and so on. And similarly, we take these 4 pixel, then we get the pixel on the top level. Okay, so so we will have two kinds of pyramids, Gaussian pyramid, and there will be two operation, reduce operation, and that will be defined like that. We will take the L minus 1th level of Gaussian pyramid and get the Lth level of the Gaussian pyramid. And the operation is again simple convolution, as we've been talking about throughout this course, that we have, so this is an image and we apply a mask and we convolve it. It's a 2-dimensional mask. This is a 5 by 5 mask, so that's why the summation is from -2 to 2, and we get the Lth level of pyramid. Now one thing you will notice that in convolution we didn't have 2 here, and 2 here is showing that the resolution is going to be reduced by half, and that's actually the reduce operation. So and for simplified notation of this will be, we'll take the GL minus 1, reduce it, and we'll get the next level, which is GL. So the operation will be similar, that we'll have this image and we'll have a window around it. Say this is 3 by 3, but we can have 5 by 5, whatever you want. You have mask, and that is the weights. We are going to talk about how to get those, and then multiply pixel by pixel and put a sum here. Then we move to the next one and do the same thing, and we'll have this convolution as we're doing this for filtering, edge detection, all those things, the program which is due today. So the now reduce operation we can explain well by looking at the one-dimensional case. If you can understand one-dimensional case, then two-dimensional is very easy, because we can use the separability property of the Gaussian, and that's why it's called Gaussian pyramid. So same thing, the only thing is this we'll call this W hat, and it's a one-dimensional mask, and this is the, say, 1/2 the row of the image. So we have only index I here, and this goes from m goes from -2 to 2. So let's say we expand this thing. Say we want to find out what is the value of pixel 2 in the Gaussian pyramid level L would depends on the Gaussian pyramid level L minus 1, because from previous one we are going to look at next one like that. So I is 2, so we expand this thing, and let's say m is minus 2, so this will become m is minus 2 here, w hat, and I is 2, 4, and minus 2 first term. Then m is say minus 1, so this is w hat minus 1, and this become 4 minus 1, and then I is 0, then this will become 0 plus 4, and then then I is 1, so w hat 1 and 4 plus 1, and I is 2, then the m is 2, and then this will become w hat 2 and 4 plus 2. So we can simplify this. This will become 4 minus 2 is 2, and 4 minus 1 is 3, and so on. So these are the relevant pixels we are going to use to compute the response at the pixel number 2. And these are the weights of the mask, and these are the actual intensity values from the previous level. So it's simple convolution in one dimension. So it looks like that. So this is the highest resolution, the lowest level, next one, and so on. As you see that in order to compute this pixel, we are going to use a 5 pixel below it. So we will have the weights. Let's say the weights are like this. So we'll multiply C with this, B with this, and A with this, and so on, add them up, and we'll get this value. And similarly for this one, we'll take these 5, this one, and this one, and these other 2, and so on. That's a convolution. And same way, if you want to compute this one, then we'll use these 5 below. So similar to the reduce operation, we have expand operation, and which is again using convolution. But here one thing you will notice that we are dividing by 2. There we will multiplying by 2. So the resolution was reducing, here the resolution will increase. And but the mask will be same. It will be the same weights, which is pretty interesting. So we will call this expand, and again the one-dimensional case we'll just use w hat p, and this is from minus 2 to 2. Then let's say we can expand for when I is 4. We can go through this different values of p, minus 2, minus 1, 0, 1, 2, and plug in I 4. It will become 4 plus 2, 4 plus 1. And now as you see that for this one we'll get 3, but this one we will get 5 divided by 2, which will become not an integer. Okay, similarly this one will become 3 upon 2 will be not integer. We don't have a pixel called 2.5 or something. So we are going to basically get rid of those which don't amount to the integer value. Okay, so then this will reduce to this term, which will become minus 2, 3, and this will be gone. Then we'll have 2, and then this will be gone. Then we'll have this one, which will become 1. 4 minus 2 divided by 2. So to find applying reduce operation, we'll take the level L minus 1 and apply this mask. We'll get level L, which has been expanded n times. This is the level L which has been expanded n minus 1 time. So we can expand several times if we want. So we can take another, say, pixel. Say we want to find out 3, what will the value of that? We can expand all this, and again we are doing this loop from minus 2 to 2. Then you will also see here some will not be integer. This will not be integer because with 2.5, this will be integer, this will not be integer, and so on. So these will essentially cancel, and then we will actually get only 2 terms for this kind of pixel. So you have 2 kind of pixel, and the one will get 3 terms, and the other one will get 2 terms, and that's fine. We are going to follow this procedure. So therefore the expand operation is as follow, that suppose this is our level L, and we want to apply one expand operation to that. So one thing is we are going to get the higher resolution, twice as much to this one, which is this one, after applying expand operation. And then to get this kind of pixel, we are going to use these 3 pixels from the top. If you get this kind of pixel, we need to use 2 pixels from the top. As you saw, 2 examples, depending on the expansion we have, because if the pixels are not integer, then they will be removed. Okay. So now the question is, what should be these weights for these the mask we are talking about? In a way, we have given some hints that these weights, which are the center one W0, W1, W2, and -1, -2, should have some property. So one is that we want to make them separable, so that we can do the convolution using 1D convolution as compared to doing 2D convolution, which requires more operations. So n square operation as compared to 2n operation, as we've been talking about. And separability is a very good property which we want to use. So therefore, this is what we want to do, and we will have 1D mask and 1D mask. We'll apply one to the rows and get the result applied to the columns. And then other thing, as it was obvious that we want to make this symmetric. So the weight at 1 should be same as -I. And that's what the Gaussian function is, as you know. So therefore, for the mask of size 5, these should be the weights. The center one, suppose, is A, and the one on the right side is B, then one on the left side will be B. The next one is C, then the one on the left side, 2 pixels from A, should be C also. So therefore, we can use these and come up with some constraints. So one thing we want to do, that these values of the mass should sum to 1. As you know, that if you take the Gaussian, if you sum them up, it will become 1. And that's nice, because if you apply a mass to the image, then if the image is from 0 to 55, then the resultant image after filtering with Gaussian will be also 0 to 55. If the masks don't sum to 1, then you have to scale all the values to make it same range. So which is fine, which is good. And second constraint we are going to put, which is important, is that all nodes at a given level must contribute to the same total weight to the nodes at the next level. So I'm going to explain this, but for the first one, sum should be, because we have 2 B's, 2 C's, and 1, so A plus 2B plus 2C should be 1. And so this constraint will give us A plus 2C is equal to 2B, and this is explained here. So let's say this is one level, and we expand this to this one, or we can say other way. So we have this one, and we have the next resolution of the pyramid is shown here. As we have talked about, that in order to compute this pixel, then we need a 5 pixels from bottom. And the way it is, the center pixel multiplied by A, the next pixel multiplied by B, and then next pixel multiplied by C. Okay, so these are the weights A, B, C, and on the left side also this pixel multiplied by B and this pixel multiplied by C. So these are the weights we apply to compute this pixel. Now if you look at the second pixel, we'll do the same thing. We take this one, this one, this one, and this one, this one. Now we are looking at the pixels from the bottom level, what weights they are contributing to the next level. So if you look at this pixel, it is contributing A to this one, and it's contributing C to this one, and C to this one. So total weight is contributing to one kind of pixel, and the top is A plus 2C. Now if you look at this pixel, it is contributing B to this pixel, and it's contributing B to this pixel. So there are actually, if you can verify that, in this there are only 2 kinds of these pixels. So one is contributing A plus 2C, other is contributing 2B. So we want to make those two pixels equal. They contribute equally to the pixel from at the top level. So that's where we get this constraint. The a plus 2c should be is equal to 2b. And that was what we stated earlier, which is shown here. The all nodes at a given level must contribute that same total weight to the nodes at the next level, higher level. So we get this constraint, a plus 2c should be is equal to 2b. Then we have other constraint that the sum should be 1. A plus 2b plus 2c should be 1. So now we can solve these to find some constraint. So suppose a plus 2c is 2b. If you put here a plus 2c, become 4b is equal to 1, which means b is equal to 1 upon 4. So we know using this the b has to be 0.25 or 1 upon 4, which is very easy. Now if we know that, then we can find out actually the value of c from one of these equations. Okay, so c is given by from here 2b minus a from this equation. If we find value of c be 2b, bring in a from here and divide by 2. So c will become half 2b minus a, and we just found out b is equal to 1 upon 4. So therefore c will become 1 upon 4 minus a upon 2, because we already have 2 here and 2 here. Okay, so this tells you we know b has to be 1 upon 4. If we know the value of b, then value of c depends on a. So therefore in this whole mass, only you have to define a. If you know a, we can define c, and b is already 1, 4, and we are done. So that's what we are going to do. So therefore, now if a is 0.4, then it will look like a Gaussian. Okay, and if the a is 0.5, it will look like a triangular. So this is a triangular kind of mask. So it's 0, then like this and like that. So a will be this much, and this is b is 0.4, and c will become small number 0. And if it is Gaussian, so then we will have these values and look like a Gaussian, as you see, as you have been looking at. So we came up with these values, defining these constraints which are intuitive, and somehow that gives us a Gaussian approximation if we select this a of this value. Okay, so we have also known the Gaussian is defined by this, and we can take the different values of x and then get a value of Gaussian there, 1, 0.6, 0.13 and 0.011 and so on, and if you plot it, looks like that. So it's all good. Now we also know the Gaussian is separable, and that's the way we have done these reduce and expand operation. So we are going to do, taking say 8 by 8 image, we need to reduce to 4 by 4. That's the pyramid. So what we are going to do, we will apply this mask to each row, and using that formula of reduce, so we are going to basically skip each of this pixel. Each alternate pixel we'll get from this row, we'll get this one, from this one we'll get this one, and so on. We'll have these 8 rows, but now we have 4 columns, because we have this in convolution we have 2i and 2j, and that was the idea there. So then we will apply one more time this mask which we discussed around each column. So again we have 8 here. Now 8 will reduce to 4, because that's a reduce operation, and then this will reduce to 4. So this way we from 8 by 8 we get 4 by 4 using the separability property of the mass which we have talked about. So it's very simple, intuitive. So then the algorithm is simple, that we apply 1D mask to alternate pixels along each row, and apply 1D mask to each pixel along alternate columns of resultant image, as I showed you, which is the 8 by 4, and then this will be the example of Gaussian pyramid. This is the lowest resolution, lowest level, the highest resolution, the next one, and next one. If you put these on the top of it, it looks like a pyramid. So now another interesting pyramid which is very useful, and you can relate this to the shift operator which we have talked about, is called Laplacian pyramid, or even Laplacian Gaussian edge detector. So the Laplacian pyramid will actually give you the pixels, which are like edge pixels. It will look like a edge image. And in Laplacian pyramid, most of the pixels are 0. And actually it can be used for image compression, and there are many uses of the Laplacian pyramid. So Laplacian pyramid we are going to define in terms of Gaussian pyramid actually. Okay, so let's say we already have Gaussian pyramid from an image. So level 1 of the Laplacian pyramid will be, we take the level 1 of the Gaussian pyramid, and level 2, which is the top one, at the lower resolution, we'll expand that. Now the resolution of this and this will be same. Then we do the pixel by pixel difference, and that will become the first level of Gaussian pyramid. Then level 2, take the Gaussian pyramid level 2, take the level 3 of Gaussian pyramid, expand that. That will then become similar resolution as the second level, subtract level 2. And just keep growing like that. Level 3 will be level 3 of Gaussian pyramid, level 2 of Gaussian pyramid, expand, then subtract. So this is the example of the Laplacian pyramid. So there was an image here, we did the expansion, we subtracted, just like that, next one. So as you see, these are actually like edge images, these edges are emphasized here. Okay. So now interesting application of this pyramid is in the compression or image coding. As you see here, what this pyramid is doing is capturing the different frequency information. We have these Gaussian pyramid, applying these different Gaussian masks. We are kind of capturing different frequency content of the image. So all these is captured here, so that probably is a better way to code the image, do the image compression. Okay, so what we are going to do, if you are given an image, say we want to show, can we compress it? Compress means we want to represent it using reduced number of bits. That's compression, like you do JPEG compression and any other compression. So the actual data size of an image is very large, but we want to compress it, and when you show the person, it doesn't look different, and that's good. So the Gaussian, so in order to do the compression or coding of an image using Laplacian pyramid, what you're going to do, first compute Gaussian pyramid, and these are the levels of Gaussian pyramid, and then from that we are going to compute the Laplacian pyramid. As we explained, this is the way it's going to go. Level 1 of Gaussian will be G1, and then expand G2, subtract, L2 will be G2, expand G3, subtract, and so on. So that's the way we have the Laplacian pyramid. Okay, so then we will code all these different levels, and then when we want to decode, we code it, and hopefully the number of bits will be less than just code, sending the Gaussian, the original image, and then we will receive at the receiver and we'll decode. So from the way we are going to decode is decode Laplacian pyramid, and from Laplacian pyramid we are going to compute the Gaussian pyramid, and we'll use the same equations as we did in reverse direction. So G4 become L4, G3 will become L3 plus expand G4, and this G2 will become like this, and so on. These are same equation, we just expand, because now here we have Laplacian, we want to get Gaussian. In the other one we have Gaussian, we want to get Laplacian. Okay, so now the last one will become the Gaussian, the first level of Gaussian pyramid, which is actually the original image. Okay, so that way we can get the image back. So the question is that why does it save number of bits? Because the coding means that we want to save the number of bits. We want to do compression. So the explanation is here. Now, let's look at this image. This is a pretty famous image of Lena, and if you get a histogram of this, it looks like that. So we have these different intensity values, 0 to 55, and this is how many pixels we have at each gray level. So as you see that this is pretty spread out, that we have almost all possible intensity values, and the histogram is like that. So which means that this as it is, if you want to compress, you will not be able to compress that much. And actually the best way you can compress this will be 7.6 bits per pixel. The regular image is 8 bits per pixel, because you have the 256 levels, so you need 8 bits. Now if you try to compress this as it is, you won't be able to do much, because we have all kinds of gray levels. So what then Laplacian pyramid is doing, so this is a Laplacian pyramid. These are different levels of the pyramid, okay? So now as you see, the Laplacian pyramid, each level, most of the pixels are 0 because we are subtracting, as you can see here. And when you get a histogram of these, they look like that. Okay, they are around 0. There are some which are positive and negative. So the way we found out that we need the 7.6 bits per pixel here, there's a very simple formula which is called entropy. You can look at the histogram, find the entropy, like the probability of particular value, and the log of that, sum it up, it gives you entropy. So that is and you can use that for Huffman coding. You can get this optimal coding using this, and that will become 7.6. Now if you look at the histogram here for these different levels, one thing is that in Laplacian pyramid we have 4 images compressed. In the original image we just have 1 image, but now here you see these are of different resolution. The one is the 1/4, other is 1/16, and so on. These are resolution is different, changing, even though we show the same size. But now the histograms are good compared to this one. This is pretty nasty histogram. It requires lots of bits. So these are actually entropies. Like in order to encode this, you need a 4.4 bits per pixel, which is much lower than this. This needs 5 bits and 5.6 and so on. Okay. Now in addition to this saving, which we are getting through the Laplacian pyramid, because most of pixels are 0, we can actually do one more thing, is to quantize this, and that's always an important step in compression, even JPEG and so on. So quantization means that like when you get a grade, so on the final exam, it's say 100 points, midterm is 100 points and so on. So we take those total points, sum it up for the whole course, and then quantize it into A, B, C, D. So we say, well, if it's 90 to 100 is A, and if it is 80 to 90 is B, and so on. So that's from the 100 possible values, which requires about 7 bits, we go to the 4 grades, and it requires only 2 bits. So that's called quantization. We take the whole range and map it to 1. Whole range, map it to 1. As we did quantization in the SIFT, that we have 360 degrees, but we bend it only 9 or 8. So that's called quantization. Okay. So like this compression, we do the quantization. So what we do, we divide by some constant number these. So now we have most of these pixels belongs to fewer bins as compared they were spread out, because we have very few bins as compared to before the quantization. So then the entropy of this will become actually less than a pixel, less than a bit, 0.77, 1.9 and so on. So this is much better than this, and it's much better than this. So if you do all that, then you can do pretty good compression. For this image, you can do per pixel you need only 1.58 bits, as compared to more than 7 bits you had. And in this one, 0.73. And one is compressed, other is not compressed, but you cannot distinguish. They look very similar. So that's the idea of a nice application of the Laplacian pyramid that you can do. So the other very good application is shown here. Let's say you have 2 images. One is an image of apple and another is image of orange. And you want to generate a new image which looks more realistic, half apple, half orange. Okay. So now if you do just you cut here, put together, it looks like that. It looks very artificial. Nobody will believe. But if you do using the Laplacian pyramid, then it looks like that, and you show it to somebody and tell that person, say this is there's a tree in Africa which will give you a fruit, half orange, half apple. They will believe it. It looks very real. And this is a very realistic image, and you can do that using the Laplacian pyramid. Okay, and it's very simple, and you can actually try this, implement in MATLAB. It's pretty easy. So you are going to generate the Laplacian pyramid of the orange image. Let's call LO. Then we'll generate the Laplacian pyramid of apple image. Let's call LA. Then you will generate the Laplacian pyramid of the combined, we call LC. And the way we are going to do that, we'll take the half of the pixels or half of the nodes from the orange, half of the nodes from the apple, and the middle one will just take the average. Because middle one we will have both, orange and apple, we take the average. And so that is a Laplacian pyramid. We are going to do this for every level of Laplacian pyramid. Okay, so then we'll take that Laplacian pyramid LC, half the orange, half the apple, middle is average, and then generate the Gaussian pyramid of that. And we know how we did that. And then the last level will be basically your, the combined thing. Okay, yeah.
So when we get the half of the nodes of the levels for LA and LO, so if this half would be changed, let's say 75% for LO, 25% for LA, so that the total image will be mostly close to orange, right?
Yeah. So if you want to make it not half apple, half orange, you make a fruit where some people like orange more. So say let's do 3/4 orange. You bite it. It's 3/4 orange and just 1/4 apple, or vice versa. You can do that. And this is just half apple, half orange. It's just you can play this game. Okay. So it's fun. It's pretty simple, very intuitive idea. So it's a very nice paper. This whole thing was taken from this paper. It's published long time ago, 1983, and also I explain this in detail the way I'm explaining in my book. So you can look at that. So are there other questions before we go to the next thing? Yeah.
About that compressing using the pyramids, do they burst better than the discrete cosine transforms in MPEG?
Yeah. So that's a good question. So it doesn't. The idea in this paper was that to demonstrate there's a new thing, pyramids and all these operations. But JPEG is pretty, has been pretty popular, and they have lots of special things. So in a way, discrete cosine transform is like a part of Fourier transform, which looks at the frequency content. So this, in a way, also looking at the different levels of frequency using the pyramid. But it has lots of other things, that how you scan, how you do run length encoding, and so on. Now the question is that these days, actually better compression you can get is from the wavelet, so JPEG 2000 and these other standards, which are using the wavelet coefficients and wavelet compression. and the wavelets actually came out of from this kind of work, the pyramids. Wavelets are much later than the pyramid work. And so that's the same idea there. The wavelets, you also have these different frequency, different filters, and you decompose this image and you encode that and so on. Okay? Any other question? No question? Okay, so now let's look at what we can do with this, coming back to the optical flow. Because the reason we want to do is that we wanted to compute accurate optical flow, and using just one resolution, original resolution of image, if the motion is large, we'll have problem. So we want to talk about Lucas-Kanade with pyramid, and the extension is very simple. So we are going to compute the we're going to compute the pyramid. Pyramid of first frame, pyramid of second frame. So we'll have pyramids. Okay. So then we will compute the regular Lucas-Kanade optical flow using the highest level of pyramid, and we assume there the motion will be small because we have reduced it. And the problem we had with Lucas-Kanade, when the motion is large, but using the pyramid we are reducing the motion by 2 pixels every level. So we'll get the highest level Lucas-Kanade. Now we are going to talk about how we can propagate that optical flow from the highest level to the next level, and so on, and keep refining that optical flow. And at the highest resolution or lowest level of pyramid, then we'll have very accurate optical flow. Okay, so one simple way will be say, well, you reduce it, to the next level, so optical flow will be divided by 2, next level divided by 4, and maybe just compute at that level and then just multiply by 4, and that you are done. But that won't be accurate. So we are going to use a pyramid to kind of do the course to find refinement, which will give us more accurate optical flow. So let's say we are at level I, and we are going to take the flow from the previous level, I minus 1, and I minus 1, and vi minus 1. So you'll have two arrays or two matrices, one for u, one for v. That's optical flow, because optical flow is a vector. At each pixel we have two values. So then we are going to kind of propagate that at that level I by first thing we are going to do is multiply the u and v by 2, because if the optical flow at the level I minus 1 is say x in the u direction, then it has to be 2x at the lower level, because the resolution is increased. So it's obvious. Now also it will happen that since we have more pixels, twice as many pixels in x and twice as many pixels in y in the ith level, we won't know the optical flow at the pixels which don't directly map to from the higher level to lower level. So we'll have to do some kind of interpolation. So I'm going to explain how to do that. Okay, so this says multiply by 2. Then the main thing, the only important thing which you have to listen to here very carefully is that we will have to, when we compute the temporal derivative, remember the optical flow involves 3 derivatives, fx, fy, ft. They are called spatio-temporal derivative. So fx, fy are the spatial derivative with respect to x and y. Ft is temporal derivative. So we are computing the optical flow, so that for that the temporal derivative is very important. So the way we are going to compute our temporal derivative, that we are going to, normally we apply these two masks, Roberts mask, we have two masks, one for the frame 1 and one from frame 2. For the temporal derivative we have all ones here, and then we have all minus 1 here. We are subtracting in temporally. So we apply the exactly same pixel in the frame 1, frame 2. But here will be a difference, that we are going to displace in the second frame, we are going to apply the displacement which according to the optical flow which we propagated from the previous level, and apply at a displaced location the second mass for ft. Then we'll subtract. And that is a way that we propagate. We know that we have some idea of optical flow which we got from the previous level. We're going to use that. And then we are going to look at the residual optical flow which maybe we were not able to compute. Okay? So I'm going to explain this further from a figure. Now, so once we know these derivatives, temporal and spatial, then we'll again apply Lucas Kanade at that level, because now we have everything. And then we will add these corrections, because at that level the optical flow which we obtain from the previous level, which is this one, which is twice as much at the ith level, and this is the residual optical flow which we computed after compensating the flow which we got from the top level. So we add that up, and that is the true optical flow at that level, and we are going to keep doing that for different levels. Okay, so that's in a way is the idea. So we're going to do this for u, we're going to do this for v. So so let's say we have two images, and we just have two levels of pyramid, just to explain simply. So this is one level, this is second level, this first image, this is second image. Okay, so now what we have, using this highest level, we computed optical flow, standard optical flow using Lucas Kanade, and we got this optical flow estimate using the method described, and this is at that I minus 1th level. Okay, so then what we did, that we took this optical flow at that point and propagated at the next level, and it will become twice as much as shown here. Okay, and but the actual optical flow, the true optical flow, was actually larger than that. It was like this, because when we reduce, so we are not able to, suppose there was 5 pixels reduced to the 4 pixel, then 2 pixels. From 5 it becomes 2, and from there it becomes 1. So we are not able to actually compute this residual one. So now what we are going to do, that since we already know from the above information the actually optical flow is at least this much, so therefore we will center the second mass of ft at this place, not at this place. In the standard way, we will take the first mass here and exactly same place second mass. But now, since we know that there is an optical flow which we know from the previous level, we are going to displace that much and put it here. And then we will estimate this residual flow, and then we are going to add that up as shown here. We compute it from this level, and we add this one to that, and we get this full one. And that's what's shown here. This is from the top level, and this is from this level, and that's the way we are going to refine. And that's it. That's the way the pyramids is going to help you to compute accurate flow. Now we can continue keep doing that different levels. Maybe you have 4 levels or 5 levels, depending on how many motion you have. Okay, so in this thing we have to do some kind of interpolation because the resolution is changing. We need to know the values of the pixels which don't directly map. So interpolation is like this. So we have, say, 2 arrays. U array at this level, then U array at this level is twice as much of the resolution, and then we have similarly for V array at this level and the next level. So now these ones which are shown in the dark circles, we can just directly map to these pixels, okay, and just make them twice as much, because now for the other ones, for example, this pixel, we need to compute the optical flow, okay, and which we'll do using interpolation. We are going to look at the neighboring pixels, like these pixels, and since we know this and so on, then we are going to compute that using bilinear interpolation. So interpolation is a very useful idea, and it's used many places, and it's a very simple thing. So let's say we have a function of one dimension, say f of x. Okay, so we know the value of function at x is equal to 1, which is say this one. We know the value of function at x is equal to 2, which is this one. Now we want to know the value of function at 1.3, 1.9, 1.5. And how do we know that? We say, well, if you know it at 1, if you know it at 2, let's assume it's changing linearly. We just fit a straight line to that, and that straight line will be like this. Then we can put in any value, we can find the value of this. That's called interpolation. Okay? And a straight line, the equation of straight line is like this, y is equal to mx plus c. So fitting a straight line means that we will find the value of m and c, slope and intercept. So since we have two unknowns here and we have two constraints, we know the f of 1 is equal to whatever value is, f of 2 is equal to whatever value this is. We get two equations from here, two unknowns, we can solve them. Two linear equations, pretty easy. So that is the 1D interpolation. Okay, it's a very simple idea, and you should know that it works very well and so on. So we can do the same thing with 2D interpolation, and here we are going to assume it's a bilinear. Bilinear means it's a linear in x, linear in y. Okay, so therefore here bilinear means a1, a2x plus a3y and a4xy. So we don't have a square term, so it's called linear. So therefore the same idea. Now here to do the interpolation we need to know value at least 4 pixels, because we have 4 unknowns. In the 1D interpolation we need to know 2, because we have 2 unknowns. So same thing, like we want to find the value at this place, and then we are going to look at the neighboring pixels, 4 nearest points. And let's say these nearest points are like this, close to the xy. So x underscore y underscore can be 1 point, x underscore x overscore and y underscores and so on. There are 4 different points, and these can be simply, we can take x and just truncate, make an integer, and there can be different ways you can select those 4 points. It's up to you. But let's say we want to find out the value of this at pixel number 3.2 and 5.6, but we have these values at integer values. So using that we are going to look at these points, x underscore will be 3 and 5 and all this thing. So that will give us that we will look at these 4 neighbors, 3, 4, 4, 5, 3, 6, 4, 6, and let's assume that at those integer value we know the values. Now we want to find out at the decimal values, 3.4, 3.2 or 5.6. So now we know the value of function at 4 points. We have 4 unknowns. We can again 4 equations, 4 unknown, we can solve those. We have these coefficients as we did in straight line. Then we can do the interpolation, and so this will be actually those coefficients for this case you can find, and these are basically differences between the point you want to find and the integer value and so on, and you get these numbers, then you are done. So that is the interpolation in 2D, and actually MATLAB will have a function which will do for you. So now if you do all that, then we can do better Lucas Kanade using pyramids. And here's an example. We had problem before. As you see here, this is without pyramid. The optical flow is not that good because the motion was large, and now when you apply pyramid you get much better optical flow because the tree is moving, the camera is moving due to that tree is moving, and we get nice. And this is the actual sequence, and this is the optical flow for this football, and then this is the tennis player and so on. Okay, any question on that? So I think it'll be good for you guys to, this is not due. I mean, I'm not expecting you to hand in, but it'll be good you write this short program to implement Lucas Kanade in MATLAB program to do pyramid and do it with pyramid, and you can get optical flow like that. It's pretty neat. It's very simple idea. Any question, comment? Just don't be hesitant to ask questions. This is you're paying money for this class, so you should get a good use of your money. Any comment? Any? Yeah.
So this pyramid can solve the faster motion or just the capacitor slow?
No, if you have a large motion, see if you have say 10 pixels, 20 pixels, so which means object is moving very fast. So that large motion you won't be able to compute without pyramid, because this whole thing depends on these mask for spatiotemporal derivatives. They are looking at a small neighborhood, so you won't be able to distinguish. So what we are doing using pyramid, we are reducing the large motion to smaller one gradually. And when we reach the highest resolution, highest level of pyramid, then that becomes very small. And we can compute, then we propagate, and then we refine, propagate, refine, and so on. So that's the idea, that to compute good optical flow, you need to use pyramid, especially when most of the time the optical flow is quite large. It's never 1 pixel or something. Yeah.
Do we have any idea what's the optimal numbers of levels for the pyramid?
Yeah, that depends on. See, the one is that it depends on what's the largest motion. If you have frames where the largest motion is, say 4 pixels, so maybe you need a couple of levels. You don't need many levels, because after if the 4 is this, then it will become 2, become 1. Okay, but if you have 20 pixel motion, then you need many more levels.
The problem is when we have a system that we design it to go through all these processes, we do not know that when the testing data comes through our system, what is the most fastest motion. So how we should...
Yeah, so I mean those kind of things are always limitations, that you have to know something about the domain where you want to apply. So there can be ways you come up with one system which works everywhere, then you can have the largest possible motion, and then there'll be more computation, but in principle it should be able to compute. You can have, say, always 5 levels, and that means that it won't be more than that, but if it's less, it will always work. Okay, any more question, comment?
Can we solve the fast motion by taking more frames?
Yeah, that's another way that, if the frame rate is large, then frame to frame motion will be small, then you can do that. And that's actually a good point. So, the typical frame rate is 30 frames per second, most of these cameras. But there are cameras which give you 200 frames per second or 1000 frames per second. But in those cases, maybe motion is very large. Like when you play golf, the way the golf moves is very lots of pixel motions. So for that you need a very high frame rate. You won't be able to do low frame rate because it will have a lot of blur. It's going so fast. The other thing is there are some videos where the frame rate is actually very low. Like I gave you an example of the CLIF data set, which is the WAMI, wide area motion imagery. We're looking at the whole city and lots of cameras. Now there's so much data, is 4 megapixel by 3 megapixel each image, so you don't have a capacity to frame, capture these 30 frames per second. So that's actually 2 frames per second. So since it's so low, 2 frames per second compared to 30 frames per second, then the motion will be very large. From one frame to other frame, huge motion. Cars are moving, so in that you need a pyramid to reduce the motion. And as you saw that, pyramid has application not only for the motion optical flow computation, it has application in finding the shift, points, because there we were looking at, that was essentially a pyramid, a little different, but the same idea, because there we were doing Laplacian of Gaussian approximated by difference of Gaussian. We were doing smoothing, we have different octaves, kind of levels, and so that we were able to capture these changes at different scales, at different frequencies. And as we talked about the HOG, human, the histogram of gradient orientation to detect people. And if you want to be able to do that at different scales, which means, it's a human, but sometime pictures taken, the human is this much, sometime pictures taken, the human is very small. So you want to have a method which can detect person any size. So how do you do that? You do basically pyramid, But pyramid will take, large size, we will make it small. So you search in all the levels wherever you can detect, and you can, use that. So pyramid scales, all these are very relevant and basic operation which which you will use again and again. And the idea is that if you understand these here very well, very intuitive level in terms of program, you can write, then you will feel very comfortable to build on these things, and that's the kind of idea here covering that. Okay, any other comment, question? So I have a meeting at 1, so with the president's review, so I think I'm going to end earlier. And so next week then we are going to talk about the motion models. What we have talked so far is how to compute the motion from image motion, the optical flow, given images. But we are going to revisit, say, well, when the motion we get from images, it's due to the motion in 3D. Objects are moving in 3D, we are capturing video and so on. So you talk about what are different models of the motion, rigid motion in 3D, and how they project to the image and the video. And then that will help us to do the next thing, how to estimate a global motion. So we will end it here.